All right, good afternoon, everyone. Can you hear me? I guess so. Um, so yeah, we're back with a slightly different topic. It's called neural simulation-based inference. It's a slightly clunky name. I think this topic might be new to a lot of you. And it's been rebranded many times recently. It used to be called likelihood-free inference, and before that, it had several other names. But you'll see very shortly what I'm talking about. So just to set the stage, what as scientists, like since the beginning of time, humans have tried to understand like what is the universe made up of. So we had people who would come up with theories like the elements that make up everything in the universe. But just coming up with theories isn't enough. There was also, interestingly, a theory of errors of empirical knowledge to so that you could quantify your uncertainties. That's what we would call it now. So it's not just good enough to have a theory. You have to also test that theory and make an inference based on data. And so today we would call the top group theorists, and these would be our experimentalists. So what are the questions we're trying to answer today? Of course, we want to know the biggest question. One of the biggest questions is dark matter or matter-antimatter asymmetry and so on. And maybe there are new particles out there that we want to discover, right? So these are things we're very excited about, and we wanted, maybe some of these can be answered at the LHC. And you know very well that these are the particles that we know of, and most of them interact with the Higgs boson, and they get their mass from the Higgs boson, which means that studying the Higgs boson is very exciting because indirectly you can probe all kinds of new physics. Yeah, okay. But our data itself in the detector is extremely high dimensional. So if you were to just count the number of sensors we have something at the order of 100 million sensors. If you really wanted to do data analysis without losing any information, we would do it in this high dimensional space. But of course, that is not possible. And luckily, we know so much about the physics process that we're able to compress this raw information into a very few set of observables. Often a single observable at the end of the day is enough to do the new physics measurement that you want to do. So to do that, we need to do density estimation. So in high energy physics, one individual event does not give you a discovery most of the time. So we want to see, for example, our simulations, we would say that this is a background only hypothesis that you would have this falling distribution. And if there were a signal, it would have this little bump over here. And then in data, of course, things are not labeled, so it's all the same. And then you try to fit your simulations to data to try to get a best estimate of what describes this kind of data, right? And we use histograms. Why? Because histograms are a really nice way to estimate these kind of densities. Even if you have finite data samples, you can populate the histogram and do this kind of statistical inference. So what we want is likelihoods as frequentists. We do all of our statistics with likelihoods. That means the P data for a given theory. And then you can compare likelihoods for the same data coming from different theories, and do your hypothesis tests that way. And turns out machine learning is actually pretty good at learning this kind of a function. Ideally, you would if you would be able to calculate them exactly. If you could calculate it, then you don't need any machine learning, any other density estimation method. You could just take your data and calculate. So in the end, you want P theory given data, which you cannot get. So we can use the Bayes rule. So this is the likelihood up here. This is the prior, which as frequentists we avoid putting any priors. The Bayesians would use that. And right. So this is the one we care about, and we want to find it. But unfortunately, up till here, you can actually calculate this. So you can get matrix elements for some process. But after that, there is, from the 4 vectors, you have to do Parton showering, hadronization. Then these particles traverse through the detector. And so you get all of these compounded terms, and then you have to integrate over that to actually get your likelihood, which is intractable. You can't compute this exactly, so you have to estimate it somehow. As I said, we do it often with histograms. But the good thing is that even though this thing is intractable, you can sample from it. That's what we call simulations. We can simulate an individual instance, which is one event, and then you simulate them many, many times. And some kinds of events you will see more often than other kinds of events, which tells you that the density is higher here compared to there, right? But this is all happening in extremely high dimensions, in this 100 million dimension space. But in the end, we don't even need the likelihood. What we really care about for hypothesis tests is the likelihood ratio, because there's this very nice statistics lemma, the Neyman-Pearson lemma, which says that if you want to compare one hypothesis with another, the most optimal way to do that is to use what is called the likelihood ratio, which is exactly this. And another thing that I hinted at yesterday was that when you train a classifier, it's secretly trying to estimate something very close to the likelihood ratio. So if you train a classifier, not exactly for signal versus background, but rather for theory 1 versus theory 2, then the classifier is trying to estimate this function. So Px, so this is per event, right? So that's why I put xi. So Pxi for theory 1, theta 1, and then the denominator is theta 0 and theta 1. And from this, you can construct the likelihood ratio just by flipping things around, right? Which means if you could train a classifier perfectly, your job is done. You can do hypothesis testing already. You don't need to do any histogram stuff and all of that. All you need is this. But of course, there's a catch. I think none of you, if I just stopped here, none of you would believe me, because we know that neural networks are not perfectly trained, and you don't want to trust the likelihood that comes from a neural network compared to a histogram method where you can really believe the likelihoods that come from your Poisson terms. So you really have to, so this is the crux of simulation-based inference, which is to be able to get your likelihoods from the neural networks directly, and they can be used in all kinds of different places. But you really, in some cases more than others, you really need to be able to trust these likelihood ratios that you're getting. And by the way, I'm talking about classifiers. There are a couple of other ways by now that you can get likelihoods. You can get likelihoods from normalizing flows, which you will see on Monday, which are generative models that actually learn the likelihood of a data set. There are also now score-based models. So the score is something like the gradient is related to the gradient of the likelihood, and so you can integrate over that and also get the likelihood. But classifiers are still really useful, because when you train a classifier between two hypotheses, it only has to learn the difference between two very similar looking distributions. Whereas if you train a generative model, it really has to learn from scratch how to construct this data set. And imagine like how much energy goes into doing our simulations, from doing the exact MATLAB computations to the detector simulations and so on. And hoping that a normalizing flow will just learn all of that perfectly is, it's ambitious. And particularly, but you will see that in fields like cosmology, they do use flows a lot. And in fact, when I work on astrophysics problems, I am using normalizing flows. But when I do high energy physics, I use classifiers. There's another subtle difference is that these generative models are better suited when you need to model the bulk of the distribution. Whereas for us, often the differences between one physics theory and another comes at the tails of distributions, where classifiers do a slightly better job. Okay. What are the kind of tricks you can use to improve the training of your neural network so that you can trust your likelihoods? One thing is while I said this entire thing is interactable, I did say this part, the first part, is accessible, right? So some of you yesterday were telling me that you're using, I think, MATLAB to calculate MELA, which is an observable using matrix element calculations. So this is exactly this. You can take your measured observables and pretend that your reconstruction is 100% perfect and plug it back into MATLAB and tell it to compute your matrix element for you. Of course, since your reconstruction isn't perfect, that's going to give you a randomness. But nonetheless, it improves your training task. So when you're training a classifier, you're giving it two labels, right? Zeros and ones. So these are your labels, zeros for one theory, one for the other theory. But the actual function you have to learn is much more complicated because the exact same event could have come from one theory or the other. So there is no way your classifier can be 100% accurate. So it's actually learning this probability function from labels that are at the two extremes, which means your labels are high variance estimators of the truth, and the thing is trying to learn something better. Whereas, if you can give it the matrix element information, then it's still not going to be exactly the same because it's ignoring all the things above. But nonetheless, your learning task becomes a lot easier because the labels are much closer to the actual function you want to learn. And it has been shown that the differences you get, so the fact that the points are not on the red line, these are randomly distributed, and so there's no bias. So it's a lower variance estimator of what you want to learn in the end. And you can think of that intuitively, it makes sense. Like once you get the Pardon level matrix elements, everything else, like from two theories, you can get the Pardon, but once you get the Pardons, everything else happens exactly the same for the two theories, right? Hadronization is the same, detector interactions are the same. The other thing you can use are gradients. So besides matrix element stuff, you can also take the gradient of that. Either nowadays we have differentiable versions of MATLAB, or you could simply fit a function and then take the gradients from that and use this as an additional loss function in your training. So the network would not only learn to estimate the likelihood ratio, but also get the correct gradient of that likelihood ratio. So what that means is if you have two things to constrain for the network, it's almost like the power of each event increases. So you become more sample efficient. All right, so where would you use these kind of methods of estimating likelihood ratios? One is, of course, parameter inference. Another very useful trick is to remove negative weights from data and reweighting. So these two are really basically, you can remove negative weights from your samples by reweighting your samples to all have positive weights. How can you do that? So you know that the cross section is not negative anywhere in your phase space, right? So if your leading order simulation says that this should be a distribution, and then your next to leading order says there's a correction, this part should be smaller and this part should be higher, then you'll have some events here. So your leading order simulation is here, and then you add some events with negative weights here to bring down this this part. I think I have a slide for this. Okay, I'll talk about it later. So yeah, so this is what a negative weight would do, but you can think of representing it differently. Now that you have, let's say you have 10 events with positive weights and 2 events with negative weights, so the total is about 8 events in this part of the region, phase space region. You could instead, you could instead reweight all the events so that they're all positive with a height equal to 8, right? So then the weight for each of them would be 8 upon 12, if I'm not mistaken, right? So this is, of course, very hard to do by hand because in one dimension you can plot a histogram and you can compare histograms and do it. But if you're really looking at this like multi-dimensional phase space, by hand doing this kind of reweighting is very hard, but a neural network can do that for you. And you can also do other kinds of reweighting. Usually in Atlas, at least, we do a lot of Pythia versus Herwig reweighting and so on. And we'll see on Monday that in fact likelihood ratios can be used for unfolding. Unfolding is when you have the measurement that you made in your experiment, but it has all the detector effects. And if you want to communicate this information to your theory colleagues so that they can use that data for all kinds of different things like constraining other theories or to fit Partha distribution functions and so on, they don't want to have to deal with your detector effects. So unfolding means removing the effects that might come from a detector. And it's a challenging problem, and there are also, we have some ways of using machine learning to get high dimensional unbinned unfolding. I'll talk more about that tomorrow, on Monday. And probably there are more ways, like likelihoods are so useful everywhere that you probably will come up with new papers using these kind of methods to solve some new challenges that you've been facing. All right, so I'm going to pause now just because I think this concept is usually new for most people. So yeah, what are your questions? Because people tend to be shy to ask, I always leave a few prompt questions. So at least you should not feel shy to ask any of these questions. Yeah. Sorry? Here? P, Z. Yeah, so let's say theta is your some theory. So it could be standard model or it could be some BSM. And so this is just like, so ZP, this is like getting a particular event, 4 vectors from that theory. And then, yeah, and then the next one is for those 4 vectors, hadronization. And then for those hadrons, detector interaction.
Okay. Ideally, I would have loved to see integral over both ZH and ZP.
Yeah, so I think it's the DZ
okay,
is everything.
Okay. So
Yeah.
it should be like,
Absolutely, it has to be.
in principle, you could have inserted many pieces of P of X given Z, and like you
Yeah,
would have extended
this is,
it.
yeah.
Okay.
This is a simplified thing, just,
Right.
yeah. Okay, good, more questions. Sorry, do I mean ZP is what?
Is the hard level matrix elements or after the Partha shower?
Yeah, let's say, I mean, yeah, I think this is just for demonstrative purposes. Like Sanmay said, you could put in a lot of more terms here. Yeah, so let's say this is really just after MAGRaph, and then okay, at some point you need to do the Partha showering and the hadronization. Let's say that's all over here. Partha showering and hadronization is here. I'm just putting it all in this, and then detector interaction.
So basically, assuming factorization.
Yeah, yeah. Assuming factorization. That's right. Okay. Right. So what I'm claiming is that you can do your final statistics and get your final results of your analysis just by taking your observed data, throwing it into the network, and giving as an additional input what theory you want to test. And the network will directly give you the log likelihood ratio, which is the final thing you use to make your fits. Of course, there's a few other steps you still have to do, like the Neyman construction. But essentially, that's it. And then then the thing is, this looks very much like a black box, right? You're used to looking at a lot of distributions, making sure, like in a normal analysis, there are so many histograms you want to look at. And here, I'm just saying, throw all of that away and put it into the neural network. Yeah. I'm sorry, I can't hear you. Can you be louder? Ah, yes. What does this mean? So it depends on what analysis you're doing. So I'm using mu's just because like signal strength measurement is often the most easy way to understand things. So let's say you're trying to do a Higgs measurement, and so let's say the Higgs signal strength could be your mu. So then you would take the observed data and you would put in mu equals 1, and the network will give you some log likelihood ratio. But here so it's a ratio, right? So it's between two theories. So the first one will be the theory you're comparing with, and the second one is the baseline, let's say, and that's going to be, I'm putting it as mu equals 1. You could use something else. In fact, it doesn't matter what you, it doesn't have to be your default. So even if your default is mu equals 1, you could put mu equals 2 here, or something unphysical, like a combination of mu 1, 2, 3. Because these are ratios, and in the end, the way you will use it is you will multiply them in a way that this term becomes irrelevant. They'll cancel out. But to train the network, sometimes the reference hypothesis, some reference hypotheses are better than others, because let's say you're training a classifier, and your new physics theory looks like this, and your reference hypothesis looks like that. Then over here you get infinities, right? So you want your reference data set, your reference data set to span the entire phase space region. So sometimes that means an unphysical simulation, which is a combination of different theories. Right, but yeah, so what is mu over here? Let's say, yeah, for Higgs signal strength, it might be mu equal, you would scan this. So you would run this whole thing many times with mu equals 0, 0.1, 0.2, to scan over the entire mu range. We'll see, I'll show you an example soon. Okay, the other thing is, now you want to make sure this network that you're going to rely on is actually well trained and well calibrated. So besides the regular ROC curves and everything you're used to, you want to look at calibration curves. This is the model score, and this is on the y-axis the fraction of positive. So like if it's a binary classification, then if between class 0 and class 1, then what is the fraction of events in your test set that are actually, if you were to look at this events with a score of 0.2, what fraction of them are actually class 1? And for a perfectly calibrated classifier, it would be a straight line. So it would be for a score of 0.2 to 20% of your events will be class 1. For a score of 0.8, 80% would be class 1. But we know neural networks are overconfident. So often you will see this kind of a curve where they overestimate their confidence both in rejecting background and accepting signal. So, and in fact, you can get multiple classifiers with the same AUC. One is better calibrated than the other. So this is something you need to really be careful about, because miscalibrated classifiers will give you bad likelihood ratios. Yeah. And then there are tricks to make to calibrate your neural network. Either you can use you can by hand fix it. You can say that if the output of the network is 0.2, I'm going to shift it back to 0.1 or something. But there are like smart ways of smoothing this out. Yeah, okay. There are another way is called ensembling, where instead of training one network, you train a whole bunch of networks and average them out, and that also helps with all of this. Okay. Yes. Another, yeah, okay, so I talked about reweighting. So if you're reweighting theory 0 to theory 1, like if you're reweighting this green one to look like the blue one, you would want to upweight events in this phase space, downweight events in this phase space. And this is a little example that you'll see in the notebook later where you actually do this. And you are able to take, so here, the green one is what I'm calling a standard model distribution. And the blue one is your new physics. These are toy data sets, so this is not real new physics. It's just a toy. And then you will train a classifier and use the output of the classifier to reweight one distribution to another. And here you can see in what color is red. The red distribution seems to match the blue one very well, even though the samples are actually coming from the green one. So it's just the weights that have been adjusted. And of course, the good thing is that it doesn't just work in 1 dimension, it works in 10, 15 dimensions as well. So yeah, you can use this to do multidimensional reweighting, unbained, remove negative weights, so on. Okay, I have this again. Yeah, so I just want to, okay, you've seen this theoretically, but I want to show you one use case quickly where, I mean, if you're wondering probably that, okay, fine, this is all very cool, but do I actually need it? Is it going to improve my analysis compared to what I've been doing already with histograms? So I just want to show that there is a use case. So going back to Higgs, yeah, so studying the Higgs is very interesting. And there's something called the off-shell Higgs. So off-shell particles are particles that have that don't have the that are not at the pole mass, they're far away. And of course, you all know this, that in quantum mechanics, particles have widths. The width of the particle tells you something about the branching ratios of the other particles it might interact with. And so if there are as yet undiscovered particles out there that are massive, they're likely to get their mass from the Higgs, and so the Higgs width is a very interesting thing to measure. Unfortunately, the standard model Higgs width is so small, it's like 4 MeV or something, which is too small to directly measure. Our detectors don't have the resolution. But you can measure it in another way, which is by looking at the off-shell Higgs. I will come to that in a moment. But another problem is quantum interference, which also you guys know very well, that if you have the same initial and final states, the two Feynman diagrams, they will both contribute to your amplitude, and there will be an interference term. So I'm just going to show you for this VBF case of Higgs to 4 leptons that so yeah, this is like simulations. If you did background only for the, okay, so it's GG to background only. This is the blue one, and then the signal is the red one. Yeah, and then the combined simulation is this pink one over here. So as you can see, the predicted number of events is actually less than the background only case, which means there's destructive quantum interference. And what that also means is that the only physical simulations you can do are with the signal and the background processes together. So this is a case where trying to train classifiers for signal versus background is not necessarily going to give you the optimal observable for your analysis. Yeah, so at least at the time when I was doing this study, the state of the art was still histograms. So you would want to construct this one sensitive observable for the signal strength of the Higgs, and then somehow fit, do the fit to data. But since there's quantum interference, there are nonlinear effects, and no single observable is going to be super sensitive. And also, this is at such high masses that you have very few events. And so if you use histograms, you are binning your events. So each time you put 2 events in the same bin, you lose information, right? So ideally, you want to do this unbinned. But of course, at the time, there was that was not something you could do. But if we need a statistical inference method that is both can handle high dimensions to handle this nonlinear effects that come from quantum interference and is unbinned, what can you do? Like, this is exactly what we're talking about, neural networks for likelihoods. And so I'm going to skip right to the end. This is some results we put out quite a few years ago now, where we compare typical observables like histograms of the mass of the 4 leptons and dijets and so on, and also a traditional machine learning method. This you can think of similar to if you had trained, like what you do in an analysis, you train a network and you use the output of the network for your measurement. That one is in red. And of course, that one does slightly better than using any individual observable. But then if you use neural network likelihoods, we see a dramatic improvement. So this is a negative log likelihood curve. So the narrower the curve, the sharper your measurement is. And we can see that with these NN based likelihoods, you can do a lot better. And this is because it's multidimensional. Everything else is a single dimensional thing. And if you haven't shown, but if you do a 2-dimensional histogram, you do slightly better even than this red line. But the thing is, histograms do not scale to 5, 10, 15 dimensions, whereas neural networks trivially do that. And okay, so this is tested for not at the standard model, this is mu equals 4. But you can also see that at the standard model, you get a dramatic improvement. And this is without using normalization information. This is with, we had to do the comparison in both cases because of some uncertainties. But the point is that it's, there is a actual use, there's a reason you would want unbinned multidimensional fits. Okay, and a final comment is that these methods, on the one hand, are very, very expensive to train because everything I told you about is training one network, but to actually get them to work, you need to train ensembles of thousands of networks. But on the one hand, the training is expensive, but the inference is super fast. You know, those of you who are in CMS know that fits can take really, really long because, yeah, statistical fits are very slow. But with the neural networks, you get the, you know how fast neural networks are to predict. So you get your likelihoods very, very quickly in the end. So it's called amortized inference, where you pay the cost upfront, and then the actual inference is super fast. So this is particularly useful if, let's say, in the high luminosity LHC, you have huge amount of data, and then you want to do this inference, you can do it pretty quickly. Right. Okay, there's another use case which I will not talk about now. I'll talk about on Monday, which is unfolding. But right now, let's jump to the tutorial. How are we doing on time? Half an hour, good. I think we're on time. Okay, so first thing, has everyone cloned the latest version? I made some changes, so you should pull the latest version of our GitHub. Yeah, I want to show. Yes, it's this one, no? Okay. Yeah, so you could even just delete what you have and do a fresh git clone of this. That would work. Or if you have the repo already, just like remove, like stash all your changes and just pull the latest version.
It's the same. It's the same repository we used yesterday. So just do git pull if you have cloned it already. If you haven't cloned, just clone it again.
And then we're going to go to this SBI folder here and open SBI tutorial 1. And while everyone is doing that, I'm happy to take more questions. I went quite quickly through the example. I don't know if anyone had questions on my slides. Yes. Yes, precisely. Okay, yeah, good question. I think this is a very important point. I'm talking about classifiers, and I'm only talking about binary classification because it's only in binary classification that you get this likelihood ratio thing. So when you are doing composite hypothesis testing, like here, we're not just testing mu equals 0 versus 1. In my tutorial, it'll be very simple. It'll be just two hypotheses that we're testing. But what I've shown here is, of course, more complicated. So here, we are testing every value of mu, right? So this is like a parameter estimation, which is a composite hypothesis test. And how can you get away with training a classifier for that? The trick is you train a parameter. So either you can train hundreds of classifiers for each value. So you could say one classifier learns to separate mu equals 0 versus mu equals 1. The other one mu equals 1 versus mu equals 2. The other one mu equals 1 versus 4, 6, 8, and so on. That is very expensive and unnecessary. What you can instead do is train one parameterized classifier. So what happens in a parameterized classifier is, so normally let's say this is your neural network, right? A simple neural network. So that's your output, Y. This is your input, X. X is your observed data. What you can do is you can give it an additional input, which is mu1. So you can say that instead of training 10 classifiers, each for some value of mu, you can train one classifier, parameterize on mu, so it learns to do the classification for all hypotheses.
So when we'll be predicting for a given set of data, we'll also have to give it some mu value.
Yes, exactly. So if I look at my, yeah, here somewhere. Yeah, so that's precisely what we're doing here. Normally, when you have a classifier, just a classifier, you would have only the observed data going as an input and something coming as an output. But here we have an additional input, which is telling it which hypothesis are we testing. And the likelihood ratio it gives will be for that hypothesis. So if I change mu here, the output of the network will change to adjust. So it's actually one network is doing the job of hundreds of networks.
So, but then it will be comparing it for a particular value of mu. It will be always finding the ratio of this particular value of mu with the sort of the null hypothesis, right?
So let's call it reference hypothesis. It could be, your reference could be your null hypothesis, but it doesn't have to be, because because in the end you're going to compute this negative log likelihood curve, and so what hypothesis you use as a reference will just be like a factor that you subtract off from the curve that you make. So it makes no difference. It's just the reference hypothesis you use is like in principle it would be a null hypothesis, but in practice it's better to give a unphysical combination.
Right,
Just
you
to
mentioned it before.
Yes. Yeah. Okay. This is all looks very cute and simple, but there's a lot of these kind of little tricks. So I really encourage you to ask questions if there's some part that you are confused about. And another interesting thing is, so I've only talked about the parameter of interest mu going in, but in our actual measurements, there's also nuisance parameters, right? Uncertainties. So how do you deal with uncertainties is not something I've talked about here. So the first paper that suggested this kind of SBI suggests to treat them as parameters of interest. So in addition to mu, you also put in nu for nuisance parameters and train it on all nuisance parameters. This is not feasible in reality, because in an experiment you can have easily 60, 70 nuisance parameters. And you're not going to have enough training data to populate the entire 60-dimensional phase space. And also, it's difficult to validate everywhere, this network. I'll show you how to validate. I'll show you a few examples of how to validate these kind of networks. Yeah, so that is like one way to do it that's been proposed, but it's not a practical way. So there are people working on making this more practical for nuisance parameters as well. Yeah. Yes. Yeah. That's I went too fast over that. So let me see. I think I don't have that slide. Let me see if I can find that slide elsewhere. Um, Okay, I'm showing you a plot from somewhere else, but it's the same study. And I show these plots to demonstrate the fact that quantum interference makes things difficult. So you can see, where is it? Okay, mu equals 4. Can you see the plot for mu equals 4 here? It's quite hard to find it, right? Because it's right underneath the background. So background means mu equals 0. Mu equals 4 and mu equals 0 are almost coinciding in that plot. This is the mass of the 4 leptons. It's one of the useful variables for Higgs to 4 leptons analysis. But on the other hand, if you look at a different plot, the delta eta between two jets, this is for VBF. Then you can see that you can separate mu equals 4 from the background pretty well, right? And so this is a random. This is mu equals 0 versus 4. For mu equals 1 versus 3, you'll have a different set of combination of variables that is optimal. For another point, there will be a different set. So the reason we can get away with doing training signal versus background is when when things are linear. So when your total expected number of events is equal to just mu of S plus B, then it's fine. So you just train signal versus background, and any excess you see in a histogram is all because of signal, right? But if you have quantum interference, it becomes more like, I think it becomes mu S plus square root mu I plus B. Yeah, where, so now the effect of mu is nonlinear, and it's not just in the total expected events, but also the shape of the distributions is different. So you can think of it like when you do EFT analyses, right? You expect different parts of the phase space not to just be some linear. So if you optimize your analysis at one point, you don't expect that analysis to be optimal at another point. So that's the point here. We are so used to this lucky case where things are linear that we forget that the general problem is not like that. So yeah, you should think of this similar to EFT analysis. In fact, SBI is really important for effective field theory measurements for two reasons. One is precisely this, that the model is now able to optimize your analysis in all parts of the phase space you want to study simultaneously, which you couldn't do before. And the other is you can measure not just one parameter, but many parameters. And in EFT setting, often you can't narrow it down to one parameter that you want to measure. We do that because we are constrained by our statistical methods, that we can't simultaneously fit 5 parameters. But with neural networks, you can. They're not uncorrelated in real life. They will affect the same phase space. Like, okay, not all the EFT parameters, but any study you do usually will have at least a few that will affect the same phase space, and then you have to have some hand-wavy argument to freeze one. Yeah.
When interference, the final result is less than the otherwise
Yes.
background, that could be modeled with negative.
Negative what? Yeah, you could parameterize it differently.
If we are desperate to have it as mu S plus B, we have to allow for the possibility that mu is negative.
Yes, that's right.
Well, I don't know what is the shape of the signal. That could be anything.
Yeah.
So anything excess, I'm open to through linear parameterization. So anything deficit I should also be open to through linear parameterization.
Yeah, but I think it'll still not work because
It won't work because
the interference.
Actually, interference isn't important.
Exactly. Yeah.
This is as simple as.
Yeah, that's right. So the mu, you could, if it was really just a deficit issue, you could have a negative mu and get away with it. But yeah, the interference really changes things more. Yeah.
If one is looking for signal strength directly, then the formula that you wrote is.
Which one?
Right.
The second one.
Plus
That's right. That's right. Where the I might be negative. I has to be negative. Yeah, here the I is negative. Yeah, and yeah, that's right. So you can't fit mu s plus b even if it was, yeah, it will give you the wrong answer. Succeed in one variable, miserably failing. Yes, yes. In each variable you have different. So that's not, yeah, so it's useless. That's right. Yeah, yeah. Yeah, in the end, one might argue that, okay, like in these kind of studies, maybe you shouldn't be sticking with the kappa framework and do the EFT framework. I don't know. I talked to theorists and a lot of them tell me this, and in the future, but this study was done in this framework, but yeah, in the future, maybe EFT framework is better. Yes. Yeah, because that's the physics. So there's interference no matter what. Electroweak is notorious for very large negative interference. Plot one diagram, your entire gauging lines goes.
Yeah, there are like a top TT bar search. If you do for scalar mediator, the mid-range pseudoscalar Higgs that has interference negative with the steady bar standard model. So you have to deal with that as well.
Yeah, okay, I'm happy to take more questions on this if required on the SBI or the use cases and so on. But just let me quickly ask, does everyone have now the notebook available? Okay, good. If anyone doesn't, please raise your hand. Okay, great. When does the session end? Okay, cool. Okay, yeah, okay, last chance. If you have any more questions about the slides. Okay, let's see what, let's try to do it in practice. So we're going to do it for a very simple problem, but it's a problem that you can actually train on your laptops and then play around with it afterwards as well. Okay, so the installation should be the same as yesterday, so you have all the packages, so we can just get started. The first cell should just run. So what are we doing here? We're generating a toy data set. It's one-dimensional Gaussian, where I think we're calling the standard model just a Gaussian with mean 0.5, and this new physics simulation we're calling a Gaussian with mean 0. Okay, and that's exactly what this code does. So we can see that they're similar. They share support mostly, but there is a difference. And we want to see if a neural network can catch this kind of a difference, and not just catch a difference in terms of classification, but really give us likelihood ratios. Okay, since we're going to do training, we need to split the data set, train test. This is trivial. Now, the reason we're doing a Gaussian example is to compare to the truth. So for Gaussians, we actually know the PDF. So we can calculate the likelihood ratio ourselves by hand analytically. That's what we're going to do first. So just a reminder of what the likelihood ratio would be is up there. And you have to fill in the boxes over here. So I have completed most of it for you. So we're making a little class that predicts the true likelihood ratio. It has one function predict. And so this SciPy stats is this thing that allows you to get PDFs for simple distributions like a Gaussian. I've used a multivariate normal here just because at the end I will ask you if you have time to do this exercise for a two-dimensional Gaussian. Right now it's, yeah, so it's a one-dimensional, but we're using this. So, okay, so to get this PDF for the new physics one, what are the parameters for it? What do I enter here? 0 and 1, yeah, that's right. Cool, good, so okay. And the next one should be simple enough. Just copy paste or something else? Yes, okay. And then the likelihood ratio is just the ratio of these two, return. Okay, now let's evaluate it on the test. Okay, it's not trained, but still let's evaluate it on the test data set because we don't need training when we know the exact solution. So here first we're going to compute it for the data set from the standard model and then from the new physics data set. Right, so this is per event, right? So first of all, you're able to get a likelihood ratio per event between the two hypotheses. And that's what's plotted here. So for the standard model data set, the likelihood ratios are a bit smaller on average, and for the new physics, a bit larger, right? Which makes sense. We don't expect them to be extremely different because the problem itself is hard. The two Gaussians are very similar, so we don't expect the likelihood ratios to go. It's not a very easy to separate problem, but we do see that on average that the standard model ones get a smaller likelihood ratio. Does that make sense? Yeah. Is there a question? No? Okay. But when you do an experiment, you don't just have one event, right? You have, often in a measurement, you might have 10 events. So then you can combine the likelihood ratios for each event for all of the entire data set. And when you multiply them together, you get more power. So let's do that here. So we can see that even though individually the differences are so small, if you combine them for the entire, like we have, I think, 1 million samples or something, if you combine them together, then the likelihood ratio of the standard model goes down to 0, and for new physics goes up to infinity, which is great. That means what this means is, if we had huge measurement, then regardless, like even if the problem is very hard, if we have enough data, we can be super confident about which hypothesis is correct. But more realistically, if we have only 100 events, then also the number is given at the bottom. So then, okay, it should be not background, but NP1 here. That's all right. Yeah. So then, even then, yes. Oh, sorry. This should be standard model. This should be NP1. Yeah. So then, for the standard model, the likelihood ratio still approaches a really small number, and for a data set with 100 events coming from new physics, the likelihood ratio is enormous. So 100 events is already very, very good. You can reduce that number and see where you start to get confused. All right. So here we're going to look at 10 events. So we're going to do a lot of pseudo experiments. So each experiment has 10 events, and we're going to see the distribution of the likelihood ratio you would get if you did this kind of an experiment a huge number of times. So I think I'm saying the number of pseudo experiments is 10 to the power 4. Each experiment we observe 10 events in data, and then we do this likelihood ratio stuff. Right? So okay, this red line is somewhat arbitrary, but you have to decide that you have to say that in your experiment, if the likelihood ratio is greater than this, then I will reject H0 and accept H1. Right? This is something you do. And so let's say for whatever reason you've chosen this red line as that point. So what this means is, so in one experiment, you will only get one point here, right? This distribution is over many, many experiments. So if your number comes over here, you would reject H0. But if the number is over here, you wouldn't. So with 10 events, you might not have the power, depending on your luck, to reject standard model or not. Yeah, so here is just to see like what fraction of the time your experiment would give you a number that's enough to reject standard model. And I think what we're seeing here is even if the true value, if you were to use this red line as your threshold, then even if the truth was standard model, you would still about 16% of the time reject the standard model. Right? So this is like statistics 101, you have both kinds of errors. So maybe you want the red line to be further away. All right. Sorry? So I think data set LRSM is the standard model data. So likelihood ratio for 10 events coming from the standard model. And it seems to be 16% of the time. It just happens to produce a likelihood ratio that passes this, that goes further right. And so you end up rejecting standard model even though the truth is standard model. So the selection of this red line is the whole thing on its own. Hopefully, like this is a, I don't want to go into a statistics course, so we're not going to talk about that. Okay. But otherwise, there's till now, yeah, everything is clear. Now the question is, okay, this is great. We can compute these likelihoods because it's analytical, but let's pretend it wasn't analytically possible. How would we estimate it with a neural network? So since the problem is easy, we're going to define a very simple dense classifier here. And you guys know how to do that, so I've not left this for exercise. We can just run this cell. And we can fit it. Now here I've left an example of an overtrained classifier, which we'll come back to later. But first, let's see things kind of work. While this training is going on, simple things next. Once we have the output of the classifier, we have the trained classifier, how do we get the likelihood ratio? Does anyone remember? What would we have to do with the classifier to get a likelihood ratio between the two hypotheses? What? Okay, one person raise your hand up. Yes. Okay. So in fact, how have I implemented it here? So the subtlety is like which one is your H1 and which is your H0 hypothesis. So if you've trained them with the class labels opposite, then that formula changes. Okay, so first thing we do the prediction. CLF.predict on X test, I suppose. And then just ravel. Okay. Like if you want this to run faster, just increase the batch size. Oh, okay, cool. All right, so I'm actually going to leave this part. Why don't you guys try to fill in this? It's simple enough. Yeah, so here you're going to, wait. This is one way to do it, but. So yeah, so you need to just fill in how to get the likelihood ratio that's predicted for all the events. That's just the sum algebra of ypred, and then run the next two cells. And so in this cell, we're going to compare the true likelihood ratio with the predicted likelihood ratio. And once you've run that, please tell me if they look similar or not. Yeah, I want you to fill that. Yeah, okay. Can I see? Yeah, that's pretty good. Okay. So at least at least one person has managed to get the likelihood ratios and they look similar. But we'll wait.
Whoever gets it, raise your hand and you can tell the values and we'll see.
Let's see what you've got. Yeah, so that's the true is on the top and the predicted, and it's 1.24, 1.29. They're not exactly the same, but like if you look at how varied the rest of them are, these two are pretty close. These two are also pretty close. Close. This one's actually pretty far, 0.36 and 41. And then again so that's for the standard model data set. Yeah. And for the new physics also, they're kind of close, but not as close as I would hope them to be. So maybe you can train the network a little bit more. Okay. So a good question I was just asked is, how close is close enough? And yeah, that's an important question, and it's not easy just to look at numbers and tell, because in the end you want to make sure the likelihood ratios are usable. And I'll show you a couple of diagnostic plots to use, like look at the physics and see if it's capturing the physics or not. But fundamentally that's a difficult, like when you do analysis with this, you spend months and months and months trying to make sure your likelihood ratios are correct. Is anyone having trouble? Their numbers look nothing alike. Are you guys able to run it? Looks good. It's running. Yeah, I would be happy with that. You got pretty good results. Nice. Yeah, okay. Seems reasonable, no? It's not exactly the same. So the question is, these kind of differences, will they have a large impact or not? Let's see. Okay. So I'm going to run it as well. What is the formula? Okay, so this is what I get for me. They're not super close, but you can see that they're like similar. 1.7 becomes 1.6. They're not super close. So if I wanted them to be closer, I might want to train a bit longer and so on. But anyway, looking at the numbers, I can't tell if it's good enough. So then we would do some diagnostics. You can look at residues, but in the end, the question is, how does it impact your measurement? Okay, so I will show you a couple of things, and you can definitely do more things to make sure. But remember that you don't want to use any diagnostics that you can't use on a real problem. So here we have the luxury to look at the truth. But in the real world, even on simulations, you will not have the true value. So you have to use only diagnostics that work for the physics case. Okay. I'm thinking we can actually follow the schedule and take a break now, and then the rest of the thing would continue.